Hello, hello, hello. How are we all? It's warm. It's warm. I'm able to get a breeze, so it's all good. It's all good. So there may be a bit of traffic noise because the window is open. It's not as warm as it was in UK, but it's warm. It's warm today. So, I need to change that. Boop-a-doop-a-doo. Whoop. Not talking about the history of rockets today. We are talking about rocket propulsions. So how they fly. Propulsions. There we go. Wonderful. How do I sound? How do I look? Ignore the hair, it's warm. Cool. Okay. Turn that down a bit. There we go. I'm not yelling into your ears anymore. So, let's get started. So, yet again today, we are going through the bronze space stuff for the RAF Air Cadets that I'm teaching tomorrow. But this is the last section, so rocket propulsions won't take too long, hopefully. I've already sorted the quiz out. They enjoy a quiz. So yeah, we'll do that, and depending on time and how hungry I am, is do I carry on and do something else? So, rocket propulsions. So we're going to talk about solid fuel, liquid fuel, and ion. And the advantages and disadvantages for it. So, starting off. So, rocket engines rely on Newton's third law of motion, as conventional aerodynamics do not work in space. Makes sense, there's no air. So, lift doesn't work. So, Newton's third law is every action has an opposite and equal reaction. So, we're pushing a lot of energy downwards to make things go up. We can burn flammable substances to provide a massive force required to launch a spacecraft into space. For smaller manoeuvres, we can use smaller ion propulsion systems, as well as liquid rockets. So most rockets have all three. They'll have a solid, a liquid, and an ion. We'll go into each one now. So this works very well with animations. I don't have that on. Can I do that? Let's have a look. New source. Windows capture. Point full. This one? It is this one. Woo! Cool, so go to that one for now, and that one. Not that one. That one. Cool. It's a bit bigger so you can see it. How do I bring myself to the front? Order, move up. Order, move to top. There we go. You can see me still. Wonderful. No, no, no. I could just... No, there we go. Fesh, that's what I am. Cool, so solid fuel rockets. These use solid propellant to burn and provide the thrust to move rocket. This is how they work. So we have a really simple shaped rocket here. So what I want to do in the future is sort of, you know those old fashioned like triangle rockets people build? I say triangle, they're most likely one triangle, they're circle. They make sense for triangle. So what I want to do at some point when I have the inclination to do it is build like a little model rocket, but on each side, so because reason triangle there's three types, three sides have the information needed on what solid fuel rocket is, what a liquid fueled rocket is, and what ion propulsion rocket is, and have it like interaction, because this PowerPoint, this whole subject is a lot of information at the kids or at the person you're teaching it to. So you can also teach it to staff. So trying to make it as interactive and get them to thinking as much as possible is what I want to do. So for the blue, so the subject that comes before this, we talk about the solar system. And within the solar system, we talk about the different planets, asteroid belt, Kuiper belt, Oort cloud, meteors, asteroids, moons, dwarf planets. So what I'd like them to do, instead of me just standing there going, this is Earth, this is the information about Earth, this is Jupiter, this is information about Jupiter, and so on and so on and so on, is I'll give them a little task to create a scale distance model of the solar system. And there's quite a good thing, like a little activity to do that. Do I have it here? No, so for example, you go through astronomical units. So Earth is 1 astronomical unit from the sun. And you just turn that into centimetres. So 1 astronomical is 10 centimetres. And you can give them the astronomical units instead of giving them the actual measurements, so they need to figure that out. And then they make a scale model. So Neptune, I forgot the order of the planets then. Neptune is like 3 metres away from your sun that you make. So that's quite interesting to show this is the scale of the solar system. Like you have some really close to the sun and then you have some really far. There's another one that I've made recently. Here it is. Which is something you can do to show how far the moon actually is. Gone on a massive tangent here. So you get like a circle or sphere. So you can get a tennis ball, basketball, whatever. And you wrap a piece of string around it 9 to 10 times. Depends on what source you get. And that is the distance from the Earth. If the Earth was this size, the moon will be that far away. And there's my little moon on both sides. And here is the reverse Earth, because I didn't do stuff properly. Look at it. Oh, I'm actually really proud of that Earth. No, that's a good little Earth. Yeah, so all I did was wrap a piece of string around this 9 times. And you can use that as a distance. At the beginning of this subject, we talk about, not at the beginning, but technically at the end, but I've moved it at the beginning, is, so we did history of rockets, but you can also do moon missions and use that as a timeline for the moon missions as well. Just make it more creative, a bit more practical, so they can research stuff, they learn it on themselves, and then you can go over it. So that's something I want to do with this as well, is either have 3 separate rockets, so they go around and try and research the information. They could do a match match the item with the rocket. Just make it a bit more interesting for them, because space is fun. I like space. So, yeah. But not today. That's not today. Today is making sure I understand this fully and not pulling stuff out of thin air. So here is our rocket tangent over. We have the casing. So the casing holds everything together. So it must be designed to withstand temperatures, pressure, and stress felt during use. Still was used for both for the space shuttle boosters. So you need something strong but malleable. You can use different materials. So cardboard is used for small models. Steel was used for the space shuttle. And sometimes it needs to be insulated because there's a lot of hot gas going on inside it as well. There you go. You can see my little mouse? Believe? Yes, you can. Woo! A lot of hot gases in here. We have then the ignition charge. The notes are not in order, which is annoying. There we go. We have the ignition charge. So the ignition charge starts the solid fuel burning by igniting it. This can be from a single electrical spark, similar to a spark plug in a combustion engine, or burning fuse like a firework. So basically, we want to set it on fire. So in a combustion engine, your engine goes suck, squeeze, bang, blow. It sucks in the air, squeezes the air to cause a lot of pressure. Little spark plug makes it bang, pushing it out, and then vacuum creates and pushes it out, creating that function of pushing things and moving the cranks and the guiding pins and all that type of stuff. And that's all they say on that one. You got the propellant drain. So in a solid fuel, so for solid fuel, it's the fuel and oxidizer has been mixed together and been set as a solid. It has a cavity within it to allow for even burning. Some have circular or even star-shaped cavities. The rate at which it burns depends on the type of fuel chosen. So it says solid fuel here, but technically, I say, you know, when you do your own model rockets and you put water in it and you put the water and then it goes whee. I say that's technically solid rockets because of how solid rockets work. Of you pump it up, it gets that, and it's a one and done thing. You can't really stop it midway. Whereas with a liquid and ion you can. Can't really do that for solid rockets. So that's why I class the water bottle rockets you use as train of thought gone. So solid, I use class as solid fuel. So the chemical reaction is depending on what fuel you use. If you want a slow burn, you'll have something that's slow reacting. If you want some fast, you'll go, ooh, give me that sodium and water. There's not a fly in here. Each space shuttle booster had 500,000 kilograms of a solid mixture of ammonium perchlorate, composite propellant, plus polybutane or chlorite. Yeah, very difficult to shut down. and everything else turns up because I have not done the animations correctly. So you got cross section. So here where it mentioned star shaped, that's what the cross section can look like. So the cavity, this is a surface of area that's exposed grain. It's normally a hollow section to increase the amount of grain exposed and available to react. A star-shaped hollow one is often used to maintain a steady burn. Yeah, so the fire goes through here. You can't see that one. Through here. And then, because you got this, so all of this stuff is being touched so it can catch on fire. We then have the seal. So the seal is the end of the casing, channeling the combustion gases to the nozzle. So it forces it into that small cone. And then the nozzle, this is shaped for the combustion gases out at supersonic speeds. From neutral to lower motion, this pushes the rocket in the opposite direction. So instead of all the gases going like that, it forces it straight line, so it forces the rocket forward. Ooh, okay. I thought I was going to sleep. Cool. That makes sense. Solid fuel makes sense to me. And it's one that people understand a bit more, especially if you are talking about model rockets that they used before. And it's quite easy to get off the internet. You can make your own. Just need a bicycle pump, something to seal the hole, and then pump a lot of gas into the water so it expands and then it goes. Oh, I don't have the video, but last time I taught this, or I didn't actually teach the course, I helped out on the course. The person leading the course brought a model rocket. I was like, oh my god, that's amazing. I loved it. And wanted to buy one for myself. I haven't. I'm tempted, but I haven't. And so some of the kids, bless them, were slightly scared. They were scared that they couldn't pump it fast enough. And I need to go and get it. I won. I weren't scared. I also had a kid offer to go, I'll go and get it for you. I was like, wonderful. It went a good couple, about nearly 100 metres. I'm terrible at distances though, so don't hold me to that. About 100 metres. Fell in some long grass. So the child, or teenager technically, struggled to find it, so I needed to walk over there anyway. So, boo me. Cool. Yeah, and I've fixed the note so it's in the right order this time. So, solid rockets have applications due to low complexity and cost. Like I said, you can make them at home. Do it in spacious room and not indoors. As the fuel is solid and stable, this means that it can be stored for a long time without specific conditions like liquid fuel. Makes sense. Need to fix that. So we've got model rockets. So these mostly use solid fuel. These are not toys, with more complex machines rising hundreds of meters. So you've got different types of model rockets. The professional one, which this image is, it's not a toy, but using the water and air can be. We've got military missiles. So our short-range air-to-air missiles are solid fuel. They're like, just go. You've got other air-to-air missiles, the ones that can change their own direction. They're not as much solid fuel. They have other propellants in there. Fireworks. You'll see them throughout the year. they're the simplest type of solid fuel rockets. If you were here on my last stream, we talked about them a bit with the invention of rockets and history of rockets. And then booster rockets, the bits that get them out of the atmosphere, because we need a lot of energy to get them up and out of the atmosphere, because Earth doesn't want to let us go. Earth wants to keep us. So it gives the space shuttle, or not technically the space shuttle, it gives the rocket the extra equipment required to get out of the Earth's atmosphere. The space shuttle one, so for those that don't know what the space shuttle looks like, this is a poor picture, there's a better picture in a second. Most powerful solid rocket motors to ever launch humans. Each space shuttle provided a maximum of nearly 1,500,000 kilogram newtons thrust, with combined mass about 1,180 tons. So a lot of energy is produced to get us out of the atmosphere. So this is what the space shuttle looks like. We've retired it. The space shuttle is no more, which is a shame, because look at it, it's so cute. So cute. So we've got advantages, and we've got disadvantages. Any ideas what these advantages could be? So, simple construction. You don't, like we said, we don't have to worry about storage. I can hear myself, don't look scary. Don't need to worry about storage. Don't need to worry about longevity. You can build these in the back garden. No moving parts. Long shelf life. The disadvantages are it's uncontrolled. Uncontrolled. As soon as you set it off, there's no way of stopping it. No way of stopping it. No way of controlling how fast it's going to go. You can't. No, that's a lie. Technically can decide how fast it's going to burn by looking at the composition of the chemical and the solid fuel. But there's no way of going, I want to add a bit more into it now. We need a bit more thrust. Need a bit less thrust. No, you can't do that with solid fuel. And it's very heavy. Very, very heavy as well. Each face. So compared to other types of rockets, moving parts. Low performance of solid propellants compared to liquid means the operator does not get as much bang for their buck as they do with more complicated liquid fuel rockets. So I'm guessing it's hard. No. Oh, what's the word? Value for money. There we go. Let's value for money. Now got liquid fuel. So liquid fuels are used propellant and an oxidizer. There's no oxygen in space, so we can contain the oxygen. Quite dangerous. They can be used to control thrusters or boosters. The tank contains fuel needed, for example, the Saturn V rockets. So the rockets that got the space shuttle up into space. And Apollo, I believe, as well. It held the liquid hydrogen, which had to be kept at high pressure to keep it liquefied. Oxygen doesn't like being liquid, by the way. So we have the propeller tank. So this tank contains the fuel needed, for example, liquid hydrogen. This is held at high pressure and low temperature to keep it in liquid form. Very cold, very cold. We have the oxidizer tank. This tank contains liquid oxygen for combustion reaction to happen. We need the fire triangle. So last time I taught this one, the kid's like, how do we get fire in space? There's no oxygen. We take the oxygen up. The oxygen is ours. So you fuel, the spark, and the oxygen to create fire. To move the propellant, so our liquid fuel, and mix it up, there are two methods to do that. We have a pressure tank. So the pressure tank is inert gas, so not gas that's not moving. Like helium, it pushes the propellant and oxidizer out of their tanks. So you can see it's connected here, and it pushes it forward. Or you got pumps. So the pumps pull things out, then mixes it up. So there's two ways. Sometimes a spacecraft, a rocket may have both, depending on what the use is, and sometimes they'll just have one. Inert, they've said it does not catch fire, which is fair. It's not used for combustion at all. Yes. We then have the injector plate. So this makes sure the propellant and oxygen are supplied to the combustion chambers in correct proportions. You don't want too much oxygen, and you don't want too much propellant, because then the force, the explosion after, it's not going to be what you want. Combustion chamber, so this is where things go boom. That's all they need to know. This is where things go boom. You got the igniter that gives the spark to ignite everything. So we've got the oxygen, we've got the fuel, there's the fire. And yet again, we have the nozzle. So the nozzle is shaped, again, to make the forces go straight, not explode outwards. So liquid-fueled engines have more control over thrust and its direction. Liquid-fueled rocket applications include control thrusters. So these one of those. If any of you watched Artemis 2 whilst it was up in space, you maybe saw like little pew 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 ever so often. Those are liquid fuel, literally just making it go. Woo, 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 woo. Main engine, so that is massive. So this is the RS-25. So 3 was used on a space shuttle, put it into orbit. Was used 135 times or 135 missions. 4 are part of the core stage of the space launch. They were put out. So this was used to get Artemis up. Then the control thrusters is a rocket engine used on spacecraft or launch vehicle for fine adjustments to altitude or velocity. Yaw, pitch and roll. So for those that don't know, yaw is sideways moving, pitch is up and down, roll is sideways. Thanks! It's a skill. I have sound effects. It's the only way I can describe things sometimes. I'm just like, who needs words? So, yeah. So, provide your pitch and roll. So, your pitch, roll. There's a little dance you can do to remember those. The space shuttle were used when heavy spacecraft require a wide range of manoeuvring during docking or with another spacecraft. So, they can do tiny little minute movements as well. The space shuttle was very manoeuvrable, and they had some at the front, some at the side. Cool. Advantages and disadvantages. So there seems like a lot more advantages here. So some of the advantages are, I'll let you think of some whilst I have a sip of my drink. more control thrust than solid fuel, yeah. More efficient thrust. Can be switched off. We can turn it off. We're good. We're just going to coast for a bit. It's like cruise control in the car. That's all I know about cruise control. And we can reuse it. Can we? A liquid rocket can be tested for. A liquid rocket can also be used to Oh, the engine itself can be reused. The flow of propellant in propulsion can be varied. Where? Liquid rocket. This is the confused face, in case you didn't know. It makes sense. I don't need to know how. I need to know why. Why are you reused? I'm guessing this is a very educational guess because a very quick Google search is not giving me the information I want. You can join me on my Google search. Bring this forward. That just works. That's quicker. Cool. So, using rocket fuel, liquids are desirable propellant because they're reasonably high density. The combustion process have. This allows the volume of propellant tanks to be relatively low. So the liquid rocket engine can be tested prior to use, whereas the solid rocket motor is rigorous quality management must be applied during manufacturing to ensure high reliability. Cool. Okay. Something's not clicking in my brain. That's the issue here. Something is not clicking in my brain. Cool. Can you read Wikipedia? Okay, guys, let me know. Liquid systems enable higher specific impulse when solid and hybrid rocket motors can provide very high tankage efficiency. A liquid rocket engine can be reused for several flights, as in the Space Shuttle and Falcon 9 series rockets, although reuse of solid motors would also effectively demonstrated through that. But how I'm guessing. So it is just. It's a car engine then. SpaceX Lancers and refuels them for reuse. I did see that. That was quite fun ages ago. So it's just it comes back down and they just refuel it like a car engine. Then that makes sense. If that's correct, please tell me. The flow of propellant in yes, I've got it. I'm smart. The flow of propellant in combustion chamber be throttled. Shut down and restart capabilities. Cool. Wonderful. Okay. Hide that again. So that's how it could be reused. Got it. It's a car engine. That's what I'm going to explain it out. It's like when you run out of fuel in your car, you put some new ones in. Disadvantages: low temperatures and high pressure storage. So storage needs to be very precise. Very complex. I wouldn't call it that complex. Oh, animations. Crisis. I wouldn't call it that complex. Maybe it is. More expensive. Yeah, it is more expensive. Would be more expensive. Mainly for storage. Then ion propulsions. So, ooh, there's a video. Exciting.
Hey, we're shopping.
There's another advert. So, whilst that is playing in the background, ion propulsion systems use positive charged atoms to generate thrust. This is where my brain goes. This is magic. This is magic to me now. So, this is an example of how it works. Example. Cool. There's our little rocket. We have a propellant tank. This contains a gas like xenon atoms. Xenon is an atom, I'm guessing. I didn't do well chemistry. Xenon. I don't want xenophobia. Xenon. Let's go with the English at Wikipedia, not the Swedish one. It's a noble gas. Just looking at it and going, woohoo! It's little 9-minute videos we can watch in a minute. Maybe do more better than explaining what I'm going to do. So I've got propellant tank. Yet again, this is not in order. So this is pumps atoms of gas into the isolation chamber. So this is just where the atoms exist. Then have the battery power supply. So the battery, this provides the electrical energy needed to operate the thruster, usually connected to the solar panels of the spacecraft. So I know to make atoms excited, you want to give them a lot of electrodes. I remember that much. We then have the cathode. Just rearranging my notes so it makes sense and I'm not there just going, ah. The cathode releases electrons into the isolation chamber. These electrons collide with the xenon atoms to remove any electrons from the atom. This creates a positively charged ion. So. Me and chemistry didn't go wrong. Before anyone says, this is not chemistry, it's to do with chemicals and atoms, it's chemistry now. So we're getting positively charged because we've took away electrons. Because you've got your neutrons and protons. More protons, positively charged, more electrons, negatively charged. I remember that much. So if we've took the electrons away, they're very positive now. They're like, yay! We then have an anode. Well, these in order. We have an anode. So these attract the electrons. So the electrons move around more. This video should, please help me, video. We then have the electronic charged grid. So these are negatively charged field, a negatively charged field from the electrical charged grid will pull the positive ions. So the positive ions are trying to get out. The electrons are just going woo, up and down. We then have, so they go out, they get pushed out, which creates the thrust. I understand that part, the thrust, exactly that. We then have neutralizer. So any spare electrons that are dumped out at the back of this system to rejoin with the ions. So like, here you go, back to you, buddy. That's it. Did we talk about the ion chamber? Or magnets? So I've got 2 extra things on here that I may end up adding. The isolation chamber and magnets, which is not talked about on here. So what we're going to do is add those in, actually. We'll do that now. No, we won't do that now. We'll watch the video first and then do that. Because that will make my life a bit more less complicated. Cool. So this one. Woo! Let's watch this and see what goes on. Can I make it bigger? There we go.
People always ask me why we're stuck with chemical rockets. Seriously, exploding a bunch of hydrogen or kerosene is the best that we can do? Good news, there are other exotic science fiction sounding propulsion systems out there which use electromagnetic fields to accelerate atoms, allowing their spacecraft to accelerate for months at a time. I'm talking about ion engines, of course, and several spacecraft have already used these exotic thrusters to perform some of the most amazing missions in the exploration of the solar system. I know, chemical rockets seem really primitive. Take tons of liquid or solid fuel, light it on fire with an oxidizer, and then use the speed of the explosive gases to give you a kick in the opposite direction. Thanks, Newton's third law. But chemical rockets do the trick. Those gases do give a rocket the kick it needs to get into space. Because they bring their own oxidizer with them, they work in the atmosphere and they work in the airlessness of space. The advantage of rockets is that they can deliver enormous amounts of energy.
Go, little video, go. So I will leave that video for now. Rearrange my screens again. There we go. So, the guy who created the ion drive got the idea from an old episode of Star Trek and wanted to call it Deep Space Nine. Makes sense. But NASA said he couldn't because there hadn't been 8 before, so Deep Space 1. Big Trekking. He's a big Trekking. I think most space people are fans of Star Trek. Deep Space One.
Energy in short periods of time. The kind of reaction you need to blast tons of cargo off Earth and into space. But they're incredibly inefficient.
Come back to you. Deep Space One. Cool. So, move this up a bit. There we go. Deep Space One was an engineering test flight for dozens of new technologies, including high-efficient ion engines and autonomous navigation software. Asteroid 9969 Braille was a bonus science target, and the primary mission was a resounding success. All 12 technology tests were successful. Cool. So, 2001. It's just there floating in space now. Is there a Deep Space 2 now? Is there more Deep Spaces? Can I eventually get to Deep Space Nine? After a successful launch into a parking... I've read that as parking lot. I was like, what? A parking orbit around Earth. A first stage burn happened on 24th of October 1998. This put DS1, Deep Space One, on a heliocentric trajectory. On November 10th, controllers commanded the Iron Thruster to fire for the first time, but it operated for only 4.5 minutes before stopping. 2 weeks later, on November 24th, 1998, controllers were once again fired. Deep Space One Iron Propulsion System, fueled by xenon gas. So this is the one that the PowerPoint's talking about then. When the spacecraft was about 3 million miles away from Earth. That's a far distance. Oh, so it's an on and then off situation then. Sort of like solid fuel, but we can turn it off. That makes sense. Like, how do we slow it down? I'll give that task to the kids. They can figure out that one. By the time the engine ran continuous for 14 days and demonstrated a specific impulse of 3,100 seconds, as much as 10 times higher than possible with conventional chemical propellants. The mission tested its payloads extensively to ensure that future users of such technologies would take unnecessary risks. DS1 passed a near-Earth asteroid, 9660 Braille. Is there multiples? Because that's a different number than before. On July 29th, 1999, I was 2. At about 60 miles. So about 60 miles away. The kids the other week were trying to figure out how, because moan about AI to them, and like data centers are bad and all that type of stuff. And I was like, yo, we could fix this. We could put data centers in space because it's cold in space. And I was like, I like the idea, but I don't know the science behind it, but I know deep down that the science is not there yet. And we Googled it whilst they had their break. Because that's a good teacher. If you don't know something, you find out for them. Or you get given them the task to find out. You don't just go, meh, push them off. So we figured it out, and it is a lot of energy still needed, a lot of cooling, so a lot of radiators are still needed, so it will be very heavy to get up there. But also, if something breaks, you can't replace it, especially not easily. So some GPU breaks, some RAM breaks. I'm just saying technology words there. They're part of a computer, I know that much. But if they break, unlike data centers on the ground where you can just go in and go, woohoo, quick swap. Can't do that in space. It's hard. It's quite hard. So the overall capacity of it will go down if one breaks. So there's thoughts about it, but they can't yet. Although it was the closest flyby to date, it's only partially successful due to a problem that compromised the data delivered to the onboard navigational system. These difficulties prevented a closer encounter originally planned at a range of 790 feet, so 240 meters. The few images returned from very long range were out of focus. Oh no. Although the data was useful, that's good. So we figured out how long or how big it was. So it was 1.4 miles and 0.62 miles in length. Once the successful primary mission was over, in 1999, NASA formulated an extension mission. Originally, the plan was to have DS-1 fly by the dominant comet 107P Wilson-Hampton, that's a long name, in January 2001, and the comet 19P Borealis in September 2001. But the spacecraft Star Tracker failed on the 11th of November 1999. Without the use of a Star Tracker, the mission was initially thought to be doomed since the spacecraft could not point ion engines or sensors in a proper direction. For more than 2 months, the operations team struggled to get the spacecraft to point the antenna forward to Earth to allow it to download data on the Star Tracker's failure, as well as other data collected by DS-1 over the subsequent. My mouth is falling apart. Over the next 5 months, I've lost where I was now. The team devised an innovative plan to revive the vehicle by building a new attitude control system that could operate without the failed Star Tracker. Although it was no longer possible to visit the bonus target given the limited capability, DS-1 was still healthy enough to be targeted to Broly, with the hopes of arriving in September 2001. By the end of 1999, DS-1 ion engine had expanded. Expended? Voyager 1 worked better. Okay. Voyager 1's still going, isn't it? It took a selfie recently, didn't it? I say recently. Set to record the largest operation experience in space. It's just going out there. DS-1 entered the coma of Comet, so that is like the dusty part, I think, from the top of my head. Yeah, I think it's the dusty part. I told this like a month ago, I should know that. Making it the closest approach about 1,350 miles to the nucleus. The nucleus is the centre part, so the coma is like the bit outside it? No. I'll Google that in a second, I know. It is the tail. The tail is the dusty part. Because you got the ion. No, the ion? So you got the nucleus, the bit around the nucleus. You've got the direction of travel, one, and then where the sun is going. Can I remember each one? No. Put the image in front of me, I'll like know it, but not coming to my head. Ice crystals, there we go. I knew it was something. That makes sense. Spacecraft's ion engine was finally turned off 18 December 2001, after having operated for 16,000 hours and provided total charge in velocity of about 3 miles per second. That's fast. The largest Delta, it says Delta 3. Delta 3, oh, we looked at this yesterday. Delta 3 is the movement, it's how fast it was going. Achieved by a spacecraft with its own propulsion system. By this point, the spacecraft had operated far beyond its planned lifetime and was running low on attitude control. I read that as it was having attitude problems. Like, it was like, no, not my real dad, all kind of stuff. A radio receiver was left on in case future contact with the spacecraft was desired. Although, in 2002, Trident was like, nah. Cool. Sure. 1. So deep space was after? Yes, deep space was after. It was in the mood, it was. It reached its teenage years. Oh, that's where it is now. Oh my god, it's so far away. Ah. Shut down an instrument aboard to save power to keep humanity's first interstellar explorer going. Is Voyager ion? It's Voyager ion. And generators? Going. Voyager 1 engine. Or propulsions, because that's what propulsions. I can't spell. Thank you, Google. Wikipedia background. Power is radioscopic generators mounted on a boom. Each generator contains plutonium generated electrical power at the time of launch, with remainder being RTGs. What's an RTG? Oh, radioscope thermoelectric generators. I can read. The power output of the RTGs declined over time due to the half-life. According to common plans, they make it to you operating at least one siren instrument to 2030. So, how does it move forward? It's a nuclear battery that uses a array of thermocouples to convert the heat released by decay to electricity. So, is it just an electric car? Are we just using electricity? For unmaintained situation at a few hundred watts. But how did it work? I'm confused. Quite a lot of things are used it. Nuclear electricity. So it's a very fancy electric car. And I don't know fully how electric cars work, so. Theft! Cool. So it uses the half-life of plutonium and makes it go forward. Does this want to work now?
A 550 metric ton Falcon Heavy is carrying almost 400 tons of fuel and oxidizer. The first stage will only burn for 162 seconds, and the second stage will fire for 397 seconds. That gives you a total burn time of
We'll watch that another day. If you want to watch it, there you go. You can watch it.
About 9.
Cool. Let's go back to the PowerPoint, shall we? Cool, so ion propulsion system produces a small amount of thrust, which over time can build the speed up to very high. Ion propulsion system's application includes manoeuvring in orbit. Satellites use ion thrusters to maintain their course and stay in orbit by using small forces. Spacecraft propulsion like NASA's Dawn was propelled by ion engines. It had a max speed of 11 kilometers per second, still fast. But it took time to get there. NASA Dawn. Interesting. NASA Dawn was NASA's first truly interplanetary spaceship. What do you mean, truly? Voyager 1 exists. It's big for you all. There we go. Can you guys read that okay? In a bit. Okay. Mission featured extended stays. Oh, Voyager is a satellite. Oh. Have you gone off a tangent with Voyager, or will you be teaching about it? Bit of both. So I'll talk about Deep Space One because that's a satellite with it, and when I read about Dawn, I'll most likely do a quick talk about Dawn. So I know it's being used. It's not some fancy science fiction things because it seems very science fictiony. Ion propulsion. They're like, oh, unlimited energy. It's not unlimited energy, but it sounds it. So yeah, we talked about satellites a couple of weeks ago. Talked about stages of satellites and how satellites work. So it's not fully a tangent. It's a small tangent, but it's not fully a tangent. A full tangent is me suddenly talking about dinosaurs right now, which I won't, because I'm good. I was looking at dwarf planets. That'll be good, because they also talk about dwarf planets on the other subject. So it all comes together. They gotta think I'm so smart, unless they find this, and then I'm like, no. Extended stays at two different extraterrestrial bodies. A giant asteroid, Vestra. I thought Vestra was a dwarf planet. Have I been lied to? He's now giving me in Swedish again. Asteroids. Only dwarf planet is more massive. I feel like I've been lied. Oh, I need to. That's a deep dive I need to figure out, because I feel like I've talked about Vesta and I don't know why. Oh, actually, I can do that now. Oh, where's my mouse? Downloads. Desktop. Basic videos. Ooh, There's a lot of things on my screen at the moment. Ceres' dwarf planet. I know that one, but I don't know why I've got Vesta in my head that it is a dwarf planet. We've got moons, dwarf planet, Pluto. Why have I got Vesta down as a dwarf planet in my head? Confusion. Yeah. I have confused it all. So it's in the asteroid belt between Mars and Jupiter. Is there no more of success? Well, that's all I'm going to look about that then. Cool. Hide that again. Let's continue. So, satellite manoeuvring is the best application to make sure the long missions interval like satellites in orbit when significant thrust is not needed, so the engine can sit doing nothing for months at a time. Then, if a satellite requires moving, maybe to avoid some debris or look at a different area. It also boosts satellites if they're in low Earth orbit. Deep space missions, so DS1. Voyager, but Voyager doesn't use it. Can be used when accelerators are not vital. And speed will come, but it will take a long time to build. Oh, fun fact. I don't know how fun fact it is for the kids, but the Imperial TIE Fighter in Star Wars is named because it has a twin ion engine. There you go. Advantages. Very small. More efficient for a small amount of fuel. Deliver longer periods of thrust. Disadvantages. Provides low levels of thrust and can only be used in microgravity, not for launch. Makes sense. So, has high specific impulse. This is ratio compared to thrust to the level fuel burnt. Ion engines uses very little fuel to produce lots of iron, so they can have high specific impulse. Because ion engines work on a reaction of pushing individual ions and elements out into space, the thrust is comparatively small. However, they can in theory work for weeks, months, or even years. Compared to a solid or liquid fueled rocket, this is a very long time. Makes sense. Because you get a lot of atoms of substance in space, it is possible to use small amounts of a chemical to do a lot. Whereas with traditional liquid fueled rockets, you need a lot. You don't get much thrust, but it works for a long time, and microgravity. Cool. I'm going to have a little 5-minute break because I need a wee. So, I'll be back shortly. I need a wee. I may grab a snack. And then we'll come back and we'll talk about how they launch. Which is really interesting because this is a bit that confuses people. Because they're like, why doesn't it go straight up? And we'll talk about that. Cool. I will see you. I'm back. Should have waited to burp till before I'm muted, but oh well. So everyone's snacked. Got a drink. Got a pee. I've got one smorgasbord left. A smorgasbord, for those that don't know, is an open-top sandwich. And these are called smorgasbords, even when I'm speaking to someone else. Because it's the only way I know the difference. Because smorgasbord means sandwich. They also have macka, I think. It means sandwich in Swedish. But this is what they call a sandwich. This is not a sandwich. A sandwich has a bottom and a top. We could get into more detail about what a sandwich is and what isn't a sandwich at some point, but not today. But this is a smorgasbord. It's an open top sandwich. So this is what I'm having for a late lunch. and my mother will be proud, because that is defrosted bread. Very chewy. Cool. So there you go, Mum. If you're watching, if you're out there, I have had defrosted bread. It's not my favourite. I miss real life bread. Not real life bread. No, fresh bread. But it works. It's something I'll live with. Oh yeah, you can see. Ooh, take it. There's all my blocks. Got my blocks. Got my dinosaurs. My knickknacks. My space books. Dinosaur books. Other books are available. Cool, so let's carry on. Of phases of launches. There we go. So, very important that this is not to scale. Because, comparatively, the Earth, if the Earth atmosphere was, this is the Earth down here. I realised you couldn't see my mouse. Ooh. There you go, you can see it again now. Wonderful. So this is the Earth down here. The atmosphere would come up to roughly where my mouse is. So not too high. Oh, it's gone. No, come back. No, you're not there yet. Come up to around about there. So not to portion. Not to scale. That is too big. But this is a new part of this subject. I haven't taught this part before, so this is going to be interesting. So, we have the vertical ascent. They don't give me any extra information on this. They've just given me this. So, vertical ascent. The goal is to rapid gain altitude to escape the dense lower atmospheric layers. Then they pitch over. Once beyond the high drag forces, the lower atmosphere, the launch vehicle transitions from vertical to horizontal. And this is where it looks weird. To build up enough horizontal velocity in the direction of desired orbital inclination. Because if it keeps going up, it gets harder. It'll then gravity turn, like a handbrake turn. The launch vehicle is now fully horizontal. It is intended inclination direction, with gravity and horizontal thrust gradually circularizing the trajectory. Vacuum phase. So once above at least 100 kilometers. So once that doesn't make. I need to reword this whole slide. Once above 1,000 kilometers, the launch vehicle engine continues its burn until it has achieved its desired velocity required to achieve dense orbit, desired orbit. So I'm going to show them a video. So this is something I've added in of the Artemis 2 launch, most recent launch, and you can see where it starts going horizontal. Here. Will we get an advert?
Välkommen till Hålands bank, Revolut, där han tjänar revpoints på sina vardagsköp som han sedan löser in mot flygpoäng och hotellvistelser. Där försvinner
7 RS-25 engines lit. 4, 3, 2, 1. Booster ignition. And lift off.
Välkommen till Hålands bank, Revolut, där han kan designa sitt kort för att matcha sin outfit.
The crew of Artemis 2 now bound for the moon. Humanity's next great voyage begins.
So it's going straight up at the moment.
Good, roll pitch.
Roger, roll pitch.
Houston now controlling the flight of Integrity on the Artemis 2 mission around the moon.
Integrity, AMT high.
AMT high.
On time, passing 30 seconds into the flights. Integrity passes the alternate MECO. Target milestone. Mission Control Houston seeing good performance on the main engines. Space Launch System core stage. Integrity, 3 miles in altitude. Traveling more than 1,200 miles per hour. Mission elapsed time, passing 1 minute, approaching max Q.
On, pumps fully on.
That's not how you get out of the
Stan, we have you loud and clear on Pond Fully on.
Have you the same?
Communication signal transfer confirmed as Integrity and its crew go supersonic. Approaching 90 seconds into the Artemis 2 mission. Integrity is 14 miles in altitude, 8 miles downrange, traveling more than 2,600 miles per hour. Minute 50 seconds of mission elapsed time, standing by for main engine throttle down to 85%, ahead of solid rocket booster separation, expected at the 2-minute 9-second mark. We see throttle down.
Cool. And then we just watch people looking at it. So that's a video I've got that sort of shows it. I'll see if I can find another one. We then talk about staging. So this is the next part of my day where I'll just research this a bit more. Because like I said, this is new. This is new. So I'm just like, huh? So while I conduct staging, and they've given me no notes, so I'll need to fill in my own notes at the moment. So why conduct staging? Typical 80% of the launch vehicle mass is propellant. So the fuel, the thing that's making it go up into the air. Once it is used, heavy empty fuel tanks remain. Each kilogram of empty tank mass carried to orbit is 1 less kilogram of payload carried to orbit. So if we take a lot of empty space with us, means we can't fill that empty space with other useful stuff like food, science equipment, clothes. There's other stuff. My brain went blank then. Aim of staging is to get rid of parts that no longer need it. So we need the most amount of fuel to get out of the atmosphere. And then we got Newton's second law. So serial staging. The lower stage ascends up to the upper atmosphere with engines optimized for atmospheric flight. The upper stage separates once the lower stage runs out of fuel and continues the launch with vacuum optimized engine. So once the bottom part is empty, it falls off. So that's serial staging, so it's like bottom falls off. Then you got parallel staging. Parallel, get my teeth back in. These are multiple boosters that are attached to the side of the core booster, igniting at launch, and then the side boosters burn out of fuel. They separate the core booster, there we go, my poor teeth. Typically, the core booster will also have an upper serial stage, which will detach for the vacuum phase for launch. So in this one, the 2 sides will go first, and then the middle one. So 2 sides, and then the middle one. So that's how rocket staging works. So what we need to look at is the staging and the launch stuff and get a bit more notes on it. Food. Cool. Oh, I've got notes again now. That's exciting. Oh, itchy nose. Itchy nose. So, why are launch sites so important? Launch sites are infrastructure required to prepare and launch a rocket. Get my teeth back in. These must be as safe as possible, minimising damage to the site or risk of life from launch, and should enable launch into the desired orbit. The limitations. There's limitations. The launch site, so the safety, should be positioned to minimise the overflight of populated areas. Makes sense. Not all nations adhere to this. This can be achieved by positioning the launch site by the coast and launching over the sea. Depends on where you are. If you're landlocked, you can't. Inclination. It is not possible to launch directly into an inclination lower than the latitude of the launch site. Due to the orbital plane intersecting with the gravity centre of gravity, orbiting the equator allows for all inclinations to reach directly reached. Okay, yeah. So if you launch from the UK, for example, you can only go up. You can go, so say UK is like 65 degrees inclination from the equator, you can only go 60 up to 90. The closer to the equator, the higher you can go, / lower you can go. I'm guessing, because it goes that way. You can go outwards. You can't go inwards. You can go outwards. Tangential speed. When the launch site is positioned close to the equator, the launch vehicle can receive a speed boost of up to 1,050 miles per hour when launching east from the rotation of the Earth. So the Earth gives it a little boost. That's nice. And then we look at different sections. So the Vehicle Integration Facility, VIF. This is the garage where the rocket is assembled, depending on the design rockets, and either stacked vertically, like Saturn V or the Space SLS, or horizontally, like the Soyuz or Falcon 9. This is to protect rockets from coastal salt air, wind, assembly, once the rocket's mated, so to say everything's put together. The payload is attached and it's rolled out onto the pad. So, it's a hangar. There we go. We then got the fuel tanks. This is where fuel is stored. Usually located a safe distance from the pad, makes sense. These large insulation spheres or cylinders hold the propellant. Common fuels are liquid oxygen, kerosene, or liquid methane. These are connected to the pad via heavily insulated pipes. The rocket isn't fueled until shortly before launch to prevent super chilled liquids from boiling away. Makes sense, you don't want it to explode. We then have the launch tower. They've actually put the notes in the right order for this one, which is nice. The tower is the surface elevator for the rocket. So the tower, it says tower and umbilicals. The tower provides structural support and access for technicians. So that's the big metal bit you see around it that goes once it's done. The umbilicals are life support lines, hoses, cables to provide provide power, data, and fuel to the rocket. While it sits on the pad, they disconnect and swing away just seconds before during this stuff. So that's how we measure stuff. We then have lighting protection. These are tall, thin masts, often connected by wires that surround the launch pad. You don't want one lightning strike, especially Florida. They have a lot of thunderstorms, and they don't normally launch on thunderstorms. But if there is a static charge, you don't want that static charge to hit the fuel, and then it goes boom. This acts as a Faraday cage because launch pads are often notorious metal structures on flat coastal areas. They are lightning magnets. These towers ensure that if the strike occurs, the electric is diverted into the ground by passing the rocket and sensitive electronics. We then have a water tower. It's not for drinking. It's part of the sound suppression system. So seconds before ignitions, hundreds of thousands of gallons of water are dumped onto the pad. Oh, so the reason they've put a bunch of water underneath the pad, I've just learned something here, is the rockets are so loud, the acoustic energy, so the sound waves can vibrate the rocket to pieces because it's so loud. And then so the water cushions everything and absorbs that. We then got the flame trench. I'm sure you saw this in films where it goes shoo. This is the exhaust pipe of the launch pad, often a deep concrete U-shaped or J-shaped channel. It directs the massive plume of fire and supersonic gases away from the rocket and pad structures. Without the trench, the heat and pressure would deflect back upwards, potentially destroying the vehicle's engines. We have the launch pad. Just thinking how this would work. I'll need to check something on that. The reinforced concrete platform supports the entire weight of the rocket. And then we have the launch mount. This holds it in place with heavy-duty clamps until the engines reach full thrust and the computer gives command to release. So, that is that. But I need to add stuff to that section. So that's what we're going to do. Whoop. And then we can open. There we go. Okay, move this back over. Cool. So, phases of space launch. Let's go into this a bit more. Oh, there's a breeze. So nice. ESA. We haven't been to ESA yet. So ESA is a European Space Agency. So the ESA launches from Europe spaceport in Kourou, French Guiana, or Russian's launch site. Kourou lies 500 kilometers north of the equator. Yeah, its proximity to the equator is ideally placed for launches into geostationary transfer orbits. And then the Russian launch sites are used for polar orbits because it's higher. It's northern. It's more northern. A variety of launchers cater to different needs. ESA's Ariane family of rockets launch large satellites into their transferred trajectories. Mama, true. Such as Herschel, Plantic, and Rosetta. Oh, that was a fun one. The Russian Soyuz rocket launched medium-class satellites such as Mars Express and Venus Express. If the spacecraft intends to rendezvous with other spacecraft, a planet, or other points in space, the launch must be carefully timed so that the orbits overlap. This is known as launch window. Weather bad, malfunction occurs during the launch window. Must be postponed until the next available window. So it depends on when the next launch window is made. They may stay on the pad for a few hours to a couple of days, or gets put back into storage because it's dangerous. Cool. That looks matsy. Talking about different rockets. Launch mass, launch size. Ooh! That works. Which one talks about Earth? One of these talk about going east to west, Earth. I think one of these talked about Earth slingshotting it. This one. Oh, there's so much information on this one already. Cool, so what we're going to do is add a slide. By not doing that, we're going to duplicate it. So we're going to get rid of this part on this. Goodbye. I'm going to see if I can add this image. So if I save the image, would it still work? This is technically a GIF. So copy, paste. It does! Heck yeah! That's just a nice visualization of it. That's good. That's good. So all those are now on the second page. So what we're going to do, bring this down here. Let's look at launch sites. Launch sites for space images. Is there a good image of launch? I may just use the one it gave me because it has all the bits on it. So copy, paste. There we go. I'm not a designer. This is talking about clubs. So what we can do now is get rid of that. Move so we don't get stiff. Yeah. Ooh, ooh. So, how am I doing this slide? I think I'll just use this and it can pop up. So I don't know what information I need for this. So or could I just make this bigger? I might just make this bigger so I can see it better. Didn't work. That's fine. There we go. That took concentration. There we go. Concentration. So now I've got information on it. And I can see it better. Wonderful. Gonna look for a video. Stages. This is only a small video.
This is the inner stage. Its whole purpose is to keep the Ares first stage connected to the Ares upper stage while we're flying on the first stage motor.
The first stage gets the vehicle off the ground, and it burns for about 2 minutes.
When the rocket gets up to about 36 miles, it actually drops away that first stage.
All the propellant in the first stage is burned up. It has nothing more to offer.
When the upper stage and the first stage separate, we've got to push the Ares first stage away from the upper stage as it continues on. So we have some smaller motors that we design and build called the booster deceleration motors to push the Ares 1 first stage away. And there we also initiate what we call the booster tumbling motors, and it initiates so the rocket doesn't just fall back straight down to Earth. We actually start it so it can tumble. We fall down, we come back in through the atmosphere, and as it's getting closer to the ocean where it's going to impact and land, we deploy some parachutes. And those parachutes will line the rocket so it's no longer tumbling, and we have a second set of parachutes that come out and slow it down just enough before we hit the ocean that we're not going to, break and ruin our whole rocket. We can do the calculations and know where those rockets are going to land in the ocean, and we tug it back to land.
Once we've separated the interstage between the first stage and upper stage, we will start the J2X engine.
The upper stage engine ignites and propels the astronauts even further into orbit.
That's useful, that was. So, how? I would like to link to this. If I and so slide insert video, online videos. Will this work? No. How do I that? What I can do? Let's put that there. Put it in the comments, the notes, and I'm like, boom, watch this. That will help me. That works. Cool. Okay. So, I am ready for my lesson for tomorrow evening now, so that is good. What I'm going to do now, because of the time, my partner's going to be home from work soon, and he's going to play some games with his friends, so I'm going to let him do that and not have me yattering on about space and maybe dinosaurs. So thank you very much for being here. If you missed a video, I've started putting them up on YouTube. So thank you very much, everyone. Is there anyone live that we could raid? Who could we raid? Can't see anyone talking about science, so we won't raid today. Cool. So, thank you very much, everyone. Thank you for being here. Oh, a raid. A raid is when we go to someone else's channel. So I'll take all the viewers into someone else's channel. So we get to watch them for a bit. If you like them, you can follow them, subscribe to them, all that type of stuff. And you can just go on little journeys to explore people, but I can't find anyone that's live at the moment. So no raids today, but next one we'll see what we can do. Thank you very much, everyone. I will see you all soon. Don't know when the next time I'm streaming yet. Maybe tomorrow, maybe not. Who knows? Cool. Thanks, everyone. Bye.